Hello, looks like I'm recording with the right microphone. Alright, today's abstract algebra 14. We're talking about the distance between a point and a line. This is quite an esoteric, or not esoteric, it's a pretty elementary topic, but it's sort of something it's a thing we need to do a lot, which is basically if you have a point and you have a line, find the closest point on the line to the point. And the way that I'm solving it today really kind of only, you can generalize it, but for now we're just talking about the standard metric, the standard geometry on two-dimensional affine space. And I'll remind you, this is the standard inner product between a vector u, or a point u, and a point v, which is the matrix multiplication of the transpose of u in the middle of the 2 by 2 identity matrix, and v. You get non-standard inner products by changing this middle argument here. And then then the standard quadrance between u and v is the standard inner product of u minus v with itself. Note this is symmetric, so the standard quadrance of u with u and v, between u and v, is equal to the standard quadrance between v and u. And I remind you, quadrance is the way that we, in our rational framework, which I stole from Wildberger, that quadrance is our way of measuring the separation between lines, and spread is our way, or other way around. Quadrance is our way of measuring the separation between points, and spread is our way of measuring the separation between lines. And today I'm just going to call this the quadrance between u and v. Alright, so given a point P, which I'm going to use a column matrix, and a line L, which is the line ABC, which corresponds to the equation ax plus by plus c equals 0. Basically two questions. Number one is find the point lambda on L that is closest to P. Find a formula for the point lambda on L. And then find a formula for the quadrance between P and lambda, which otherwise is the quadrance between the point and the line. Alright, so just here's a diagram of what we're doing. So you have a point, you have a line, we want to find this closest point. You should expect a right angle, because if you kind of deviate from this, the length gets longer. Different inner products will have differing notions of right angle, so it doesn't always correspond to this picture, so you have to be a little bit careful. So the strategy I'm just going to use calculus, because that's the most straightforward and obvious way to solve this. So the way that we're going to solve this, you find any point little l on the line big L. You write L as a parametric function of some parameter t, which you can think of as time. So you pick L, that's gamma of 0. So you were writing gamma of t as L plus vt, where v is a vector that is parallel to the line. And so gamma of 1 is this point, gamma of 2, you just add v again, gamma of 3 is up here, gamma of minus 1, you do minus v. And t is rational, not doing that real number nonsense. Then write a formula for little q of t, which is the quadrance between p and gamma of t. So, p is up here somewhere, and for every point t, this q of t measures the quadrance between p and gamma of t. So wherever gamma of t is, it's a particle along this line. This function little q of t gives the quadrance, which is distance squared, remember that. So you can realize that if you minimize distance, you're also going to minimize distance squared. So that's the way I'm thinking about this. And then minimize with respect to t. Alright. So we're just going to use calculus. So we have a couple special cases. Number one, if p is on the line, then the answer is p. Duh. P is obviously the closest point to itself on the line. If L, right, I'm going to want to write this as y equals L. Generally want to write L as y equals mx plus b, so you need to eliminate the case where you can't do this, which is with vertical lines. So if we have a vertical line, again, this is just the standard geometry. Wildberger, I think, calls it the blue geometry on the Euclidean plane. This is where you have a line that's x equals foo. Then, well, p is equal to p1, p2. You just move over to foo p2. Okay? Then the point foo p2 That's the answer. Again, only with our standard inner product, and different inner products you're going to get a little bit, you have a different notion of do this translation thing. All right. General case, we have a line L, which is ax plus by plus c equals 0. B is not equal to 0. So here was ax plus 0y is equal to c, or plus c is equal to 0, in which case x is equal to minus c divided by a. All right, we rewrite this as minus by is equal to ax plus c, or y is equal to minus a over b times x plus minus c over b. All right, well, the point L is equal to 0 and minus c over b. Just plug that in, you'll see. That's definitely on the line. It satisfies this equation. So we let our vector v be 1 and minus a over b. So, right, so the picture for this is we go 1 over and then the slope of the line up, because the slope is rise over run. So if we have a run of 1, then we'll have whatever the slope is of rise. Because rise over run, if the run is 1, then the slope equals the rise. So here's the picture. So L is our point here, which is 0 and minus c over b. Right, because every line that is not a vertical line intersects the y-axis. So that's going to be gamma of 0, and then gamma of 1 is just going to be going over 1, gamma of 2 is going to be going over 2, gamma of 3, gamma of 4, gamma of minus 1, gamma of minus 2, gamma of minus 3. This isn't a great picture, but you see what I mean. So gamma of t is L plus t times v, right? Just what we're doing. So we start here, and then we can go to the right or to the left based on the parameter t, which is, if we plug it into the original equation, or if we just do L, which is 0 and minus c over b, plus t times v, we get the vector t and minus c over b plus minus a over b times t. All right, well, let's just plug it into the original equation to make sure it works. So here's our original equation. I wrote it as a matrix product. AB times t minus c over b plus minus a over bt is equal to minus c. So same equation as above. I just rewrote it in a slightly different way. Well, we expand this out. The a times t plus b times, I did 2 steps here, plus b times minus c over b plus b times minus a over b times t. Well, these b's are going to cancel, so we get at minus at, b's are going to cancel, minus c, so we get minus c equals minus c. So we're done. All right, we're defining q, so q of t is equal to q, the quadrants between this point and this other point. So quadrants between p1, p2, and t, and minus c over b plus minus a over bt. And of course, this is going to be equal to p1 minus t squared plus p2 plus, notice the sign flip because we're taking a subtraction here, plus c over b plus a over b times t squared. And then differentiate this with respect to t using the chain rule. This is going to be, you pull the minus 1 out here because of the minus in front of the t, and the 2 comes down. Minus 2 times p1 minus t plus 2, the a over b comes out. The 2 comes down because of the exponent. The a over b comes out because of the chain rule. Times p2 plus c over b plus a over b times t. So 0 is equal to t. So I'm just grouping t terms. So we get minus minus 2 t terms over here, and 2a squared over b squared t terms from over here, plus all the things that aren't t. So we get minus 2p1s plus 2a over b times p2, that's from over here, plus 2ac over b squared. How do we get that? Yeah, this 2a over b times this c over b term. That's how we get 2ac over b squared. Note that this is an 2 plus 2a squared over b squared. That's always going to be positive. So the curvature is positive. which means that this is a function that curves upwards. That's what positive curvature means. That's the second derivative, positive curvature. So if we differentiate this again, we're just going to get whatever is under this blue brace here, or whatever is on top of the blue brace. That's what we're going to get as the second derivative. So that's also called the curvature of the function. If the curvature of the function is positive, then the this derivative gives the slope. If you're not familiar with calculus, sorry, this derivative gives the slope at any point of the at any point t. This gives the slope of the tangent line of q of t, and the minimum or maximum, the extremal points, will occur when the tangent is horizontal, i.e. the slope is 0. That's the idea. That's like the idea of calculus, is that that's how all optimization works, is based off of that. So anyway, the second derivative is the rate at which the slope is changing. So if the slope is going from negative to positive, then it's going to be a minimum. So if the curvature is positive, the function curves upwards. Then when we solve for this horizontal tangent line here to this function q of t, then it will definitely be a minimum. And I drew a really kind of conceptual graph here. Please don't read too much into this graph. P, q of t, L, and this axis denotes t. So we're traveling along L. And so I rotate it. Probably this is this maybe is a graph in the special case where L is a horizontal line. Don't read too much into this graph. I'm just trying to illustrate the point, which is that this is definitely going to be a minimum. You have a problem, which is that when you solve for a horizontal tangent, you can't tell if it's a minimum, a maximum, or an inflection point. So the way you tell is by taking another derivative. If your derivative is positive there, then it's definitely a minimum. All right. So you rearrange this equation in terms of t, so you get t is equal to minus. So we move this stuff inside this brace over to the other side of the equation and then divide by the stuff over the blue brace. And we get minus 2p1 plus 2a over bp2 plus 2ac over b squared, all over 2 plus 2a squared over b squared. And then we simplify a little bit. We pull a minus 2 out of this top equation, and that cancels this minus sign here. And we get p1 minus a over b p2 plus ac over b, or minus, let me try reading that again. p1 minus a over b p2 minus ac over b squared. So all I did was pull minus 2 out of this brace. And then that cancels with the 2 on the bottom, and we get 1 plus a squared over b squared. Well, clear fractions, so you multiply top and bottom of the fraction. If you multiply the top and bottom of a fraction by the same thing, as long as it's not 0, because you can't divide by 0, and 0 over 0 doesn't make any sense. If you multiply the fraction top and bottom by the same thing, that's equivalent to multiplying by 1. So you get b squared p1 minus ab p2, so I just multiplied by b squared, minus ac all over a squared plus b squared. Okay, so that's our that's our value of t, and lambda, if we scroll back up to our idea, so what I did is I plugged, what did I do? Right, so this is, maybe we should call this like t hat or something. And so gamma of t such that this little q function is minimized is this value lambda here. So this is the closest point. This is the formula for the closest point. I solved for the value t such that gamma of t will be the closest point to p. Let me scroll back up to the original graph. Right. So I solved for this function. So we parameterized this line L by gamma of t, and then I solved for the t value that corresponds to this point lambda. And all I'm doing down here is writing down the formula for lambda, which is our first problem. All right, which is b squared p1 minus 8. I'm just going to read it again because I ended up memorizing this formula writing these notes. B squared p1 minus ab p2 minus ac over a squared plus b squared. And then, right, so maybe pause the video or like split screen, open a new window or something. Minus c over b, I'm tired of scrolling. Minus c over b plus minus a over b, that's going to be the second, this is going to be the second coordinate times the same thing in the first coordinate. All right. And this is going to be on the line L because we take a times the first plus b times the second. Well, the b will cancel with the b in this fraction. And so it actually doesn't matter what you put in here. Right? That's the idea with the t. Doesn't matter what you put in here. A times the first plus b times the second. Well, the b will cancel out and you just get minus c no matter what. So it's definitely on the line L because this is a perfectly valid value of t. All right, so this constitutes a proof, but it's kind of opaque. So let's just try some special cases. So here is a horizontal line. Y is equal to 3, which corresponds to 0x plus 1y minus 3 is equal to 0. And we want to find the closest point to on this line to the point 2, 0. Well, if we just use our intuition, it should be 2, 3. So let's check. So write out all the values. A is equal to 0 because that's the coefficient for x. B is equal to 1, that's the coefficient for y. And c is equal to minus 3. P1 is equal to 2, that's the first coordinate here. And P2 is equal to 0, that's the second coordinate. All right, lambda 1, we just plug it into the formula. So b squared P1, that's 1 squared times 2. Minus 0 times 1 times 0, that's a times b times p2. Minus 0 times minus 3, that's minus a times c. Over 0 squared plus 1 squared, well, that's 2 divided by 1, so that's equal to 2. We got the right answer because we're looking for 2, 3. Lambda 2, we take minus c over b plus minus a over b times lambda 1. So this is minus 3 over, this is 3. That's the answer, it's 3. So we get the right answer. All right, let's try x plus y is equal to 1. So that's equivalent to y is equal to 1 minus x. That's this line right here. A is equal to 1, b is equal to 1, c is equal to minus 1, and we want to find the closest point to the origin. Now, if we just look at it, it should be a half. That should be the answer. All right, so lambda 1, that's b squared p1 minus ab p2 minus ac over a squared plus b squared. All right, and that is equal to, well, we have, yeah, we just plug in 1 squared times 0, so that's b squared times p1 minus a times b times p2, which is 1 times 1 times 0, minus a times c, which is 1 times minus 1, over 1 squared plus 1 squared. Well, the only non-zero term here is this, which is minus 1 times minus 1 over 2, so this is a half. Got the correct answer. Lambda 2 is minus c over b. This should be a plus here, sorry. Lambda minus c over b plus minus a over b times lambda 1. That's 1 over 1 because c is minus 1. 1 over 1 plus minus 1 over 1 times a half, which is 1 minus a half, which is a half. Got the right answer. All right. And then I wanted to show you that this works actually in the special case I outlined above, where the point is on the line. So y is equal to 3x plus 4, so it kind of looks like this. 3x minus y plus 4 is equal to 0, so I just rearrange the equation. P is equal to 0, 4, which is definitely on the line. All right, so we have a is equal to 3, b is equal to minus 1, and c is equal to 4. P1 is equal to 0, P2 is equal to 4. P1, okay. Lambda 1, same formula as before, but I'm going to say it again. b squared p1 minus ab p squared minus ac over a squared plus b squared. Plug in all the values. I'm not going to, well, yeah, I should read it. Minus 1 squared, that's b squared times 0, so b squared p1, minus 3 times minus 1 times 4, which is a times b times p2, minus 3 times 4, which is minus 12, all over 3 squared plus minus 1 squared. So we should expect this to equal 0. And indeed, we get 0 plus 12 minus 12, so that's 0 over, it doesn't matter what the denominator is, but it happens to be 10. All right, and that's equal to 0, so we're good. All right, and then lambda 2 is equal to minus c over b plus minus a over b times lambda 1, which is, of course, just going to be minus c over b, which in this case happens to be minus 4 over minus 1, which is 4, so we got the right answer. All right, so this even works if the point is on the line. All right, and finally our quadrants formula. I didn't actually write out the quadrants formula. I wrote out a recipe for how to get it because I kind of ran out of steam. All right, and then what the hell is squipple? Standard quadrants between a point and a line. That's right. Standard quadrants between a point and a line of a point, P1, and then this dash means I don't care, and a line A0C. Well, if we go back up to our, where is that diagram? This diagram. Well, the only distance that the only quadrants that matters here is this, because there's no difference in the y-coordinate. And so this is going to be P1 minus foo quantity squared. And that's all that's going on down here. Right, where are we? Right. Oh, boy. Right, so this, oh, I wrote this as a, so ax plus 0y plus c is equal to 0. That's equivalent to x is equal to minus c over a. Rearrange that equation. Do it on a piece of paper if you don't believe me. So I wrote it in S expression notation. Square of the subtraction of p1 and the division of minus c and a. Or in more standard mathematical notation, p1 minus c over a quantity squared. So that's right. So the line is the line x is equal to minus c over a, and then the point has x coordinate p1. So the only thing that matters is p1 minus c over a quantity squared. That's going to be what the quadrants is. All right, and then we have this is for the special case of the vertical line. For the non-vertical line, the standard quadrants between a point and a line of a point p1, p2, and a line ABC. This is defined as, okay, I wrote down a recipe here and I left it as an exercise to the viewer because I got lazy. But it's fairly obvious how you do this. You write down the same formula for lambda 1 and lambda 2 that we have above, but I'm going to read them again because it's worth repeating. Important things are worth repeating. B squared p1 minus ab p2 minus ac all over a squared plus b squared. That is lambda 1. Lambda 2 is minus c over b plus minus a over b times lambda 1. And then our quadrants is, of course, going to be just the quadrants between p and lambda, which is p1 minus lambda 1 squared plus p2 all squared. And then maybe an exercise is expand this out, see if you get a simpler formula. This is good enough for me because I can write a program to do this. That's my standard, by the way, is can I write a program? I don't like distance and angle and all these other ideas. I like writing programs because that's a really good way to convince yourself of something and to really work through the logic of how something works. A computer is the dumbest thing in the world. It's like the, computer has, grade A autism. It literally will only do exactly what you tell it to do, and sometimes it won't even do that. And so if you can write out your idea as a computer program, that's really the best way to understand it, to make sure that you've really ironed it out and that there's no ambiguities if you can write it as a computer program. And my friend Craig Cannon, great quote, I can't say it on YouTube, I don't want to curse. If your idea is not computable, it's horse manure. That's what he said. And he's a programmer. He's not a math guy. I am going to be talking about this because the reason I bring that up, or the reason I remember that quote, is because he said it during a podcast that we did. And I just finished, watching the podcast and putting in timestamps. And anyway, that relates to WFC, my other thing that I'm doing right now. Because that was the presentation that I'm giving in the WFC playlist. It's largely just the same presentation I gave to him in that podcast. Anyway, that was something he said during that podcast, and it was a lot of fun. It lasted 9 hours, and that was it was a lot of fun to do, and it was very painful. Not painful. It was just like it's 9 hours, and reading through or watching through it again and doing timestamps, and then I texted Craig and said, "Hey, you said X, Y, and Z. Do you want me to edit that out?" And then I didn't, and of course I didn't mark down where he said X, Y, and Z, and he said, "Oh yeah, please edit that out." And of course, so now I have to go back and watch it again or try to find where he said that. Anyway, it's going to be a lot of fun. This is blocking the WFC playlist, so that's why I'm working on this, is because I want to, in the WFC playlist, link to the podcast, because I think it's good, because Craig's a really experienced, talented programmer. He actually wrote the chat server code that I used to make the telnet server for WFC. So if you want to play with WFC, let me blow this up. Write out WFC in terms of the letters. W is the 23rd. W is the 23rd letter. F is the 6th letter. C is the 3rd letter. And you can play with a little Lisp shell here. Here's some documentation. Right, and this is equal to 1. And watch my WF Algebra playlist if you want to understand this, or once I get around to clipping up the podcast, watch the podcast, because I hadn't written this thing yet, but I had written the library that this uses, and so I walked through the logic completely of how this works, and then we actually go through every single line of code in the library and go through how it works. And Craig is a much better programmer than I am, and so it's code review by somebody who really knows what they're talking about, really knows their stuff. Anyway, I am getting completely off track. This hasn't actually, it does relate to this, but sort of in a very long way. I'm thinking about what else do I want to talk about here. Craig now works for what does he work for? He works for some cryptography cryptocurrency firm, and he wanted to do a thing where he walks me through a lot of stuff about how his cryptocurrency, their crypto thing works, and so I wanted to brush up on cryptography before I do that, and it actually fits into abstract algebra, because algebra is sort of generalized arithmetic, and the mathematical term for arithmetic is number theory, and cryptography is all based on number theory. And so in a way, number theory or arithmetic is sort of the most important. It's where abstract algebra comes from. It's the most important instance of abstract algebra. If we want to talk about concrete examples, I'm all about concrete examples. I'm all about show you what's going on, give you some concrete examples. And really the most important examples of, we're going to be talking about groups and rings and fields. The most important examples all come from number theory. They also come from linear algebra, but also, historically more from number theory. I actually don't know the history, so please don't quote me on that. But I think historically from number theory, because, Fermat precedes Galois by a number of years, and Galois is sort of the father of abstract algebra, maybe. Galois and Abel, maybe? I don't actually know. Please don't quote me. Please don't sue me either. Just generally don't sue me. But anyway, if we want to talk about applications of abstract algebra, first of all, there's a ton of applications that, for some reason, people don't talk about. We can actually use it to do calculus. We can use it to do a lot of things. We can use it to do topology. It's algebraic topology. Oh, I should redo the homology video in terms of Gaussian elimination, because all it boils down to is Gaussian elimination. Anyway, I want to talk about some number theory and then get to how a bit of cryptography works, and then maybe talk about cryptocurrency on this. I'm not really sure, because the important part about cryptocurrency is not even the cryptography. I mean, that's certainly an indispensable part of it, but the cryptography was not the new idea. The new idea was the consensus algorithm. Then there's new ideas with specifically the cryptocurrency that Craig works on, and I don't really understand that. He will give me some long nonsense. It's not nonsense. But Craig's certainly a person worth listening to. I'll try to remember to link to his Rumble channel down below, because he's a brilliant guy, really worth talking to. He should be very famous just on account of his brilliance. Anyway, that got off topic. Anyway, I will see you in the next video. Have a nice night. Thank you for watching. Bye.